Okay, so we're going to move on to a short little lesson about bases and calculating Kb. So you'll find this information very similar to what we did with acids and Ka calculations. So I think you'll pick it up pretty quickly. It doesn't differ all that much. So first of all, let's compare strong bases to weak bases and look at the difference between them. So just like strong acids, strong bases dissociate almost completely in water. So for example, if you mixed sodium hydroxide, which would be a solid, I'm just going to switch up my pen here so we can see this a little better. Okay, so this would be a solid. If you mixed that with water, so stirred it till it dissolved, when it dissolves, it dissociates into the hydroxide ion and the sodium ion. Okay, and it dissociates almost entirely, meaning this completely separates into its individual ions. That's why we just see the single arrow as opposed to the double-sided arrow. So almost all of the NaOH dissociates, or you could say ionizes, into OH negative and Na plus ions. So if we did KEQ, so remember KEQ, we've been doing all different varieties of KEQ. We've started with KEQ, then we looked at KW, Ka, and now we're going to look at Kb. So if we're just looking at how we would express it for KEQ, the only two that we would express here are the ions, because the sodium hydroxide is a solid, so its concentration doesn't change. So I would put OH, the concentration of OH negative multiplied by the concentration of Na plus. And when you calculate that value, you end up, for strong bases and NaOH as one of them, you get a very large value for KEQ. Okay, and the reason for that is because as this reaction progresses, you get mostly ions. Okay, and it's happening just in this forward direction. So KEQ for a base, we have our own specific constant that we use for bases, and it's called the base dissociation constant, and we use the symbol Kb. So very much like Ka, it's just this one is particular, or it's designed to represent bases. So a strong base has a large Kb value, and it would also have a high pH, so in the 13 to 14 range on the pH scale, right? So remember, bases range anything above 7 up to 14, so a strong base is in that upper limit of the pH scale. So strong bases include anything with cations from the alkali metals family, so sodium, lithium, and potassium ions in particular, and also from the alkaline earth family, calcium, and magnesium in particular. So those result, when those combine with a negative ion or with a OH negative ion, you end up getting a strong base. Weak bases, on the other hand, just like weak acids, very little of the base will dissociate. Okay, so with a weak base in water, you have mostly base particles in solution with very few OH negative ions. So Kb for a weak base is very low because barely any hydroxide ions are made. So let's look at a weak base example, ammonia in water. Okay, so ammonia would be in the gas state. You can dissolve a gas in liquid water, and when you do that, it will ionize or dissociate to some extent into hydroxide ions, and then the other ion would be NH4+, which is the ammonium ion. Okay, so notice compared to the strong base, the weak base has the double arrow. This will dissociate, but only a very, very small amount. Most of it will stay as NH3. So for this one, to calculate Kb, we would take our product concentrations and divide by, in this case, we do not use water because it's liquid, but a gas has a variable concentration, so you can use NH3 on the bottom. And when you calculate the Kb value, you get 1.8 times 10 to the negative 5, so quite a small value. So if we were to just diagram out NH3 in water, make it in a little beaker. Okay, so here's our beaker. This is going to be our solution. What you'd mostly have is NH3 floating around all throughout. And then you'd have just a small amount of the ions. So I'm just going to show that with just one of each ion amidst a sea of NH3. Now I'm just going to circle these so that they stand out. So it's just showing that there's just a very small amount of ions, the rest stays intact. So this is just a chart of some weak bases. It gives the name, the formula, and the Kb value. So again, they all have really small Kb values, and there's just kind of a array of different ones there. So let's do some calculations with Kb. You'll see that these are very, very similar to the Ka calculations. We go about solving them in the same way. So our little ice chart comes back into play again. So it says calculate, the first type of Kb problem would be calculating the hydroxide ion concentration when you have the value of Kb. So this one says, what is the OH negative concentration of a 0.4 mole per liter ammonia solution? Set up an ice chart and substitute equilibrium concentrations in. So first let's write our expression. So we have ammonia. We're going to mix that with water, liquid water, and it's going to somewhat ionize into hydroxide and the other. So basically think of it this way. The water is losing a hydrogen, and that hydrogen hops on to here, right? So this is the base, so this is the proton donor, the acid. So you've got an H plus making its way over here. So that leaves the water as just OH negative, and that would change NH3 into NH4 plus, okay? So we're told that the ammonia solution is 0.4 mole per liter. Initially, the ion concentrations would be 0. And we can just use x's in this change, just like we would have done with a Ka. So this one is going to change by negative x, and these two positive x. And again, this is all a 1-to-1 ratio, so we don't need to add any coefficients or anything in here. And then these guys just become x's, and this would be 0.4 minus x. Now, just like we did with Ka, we're going to disregard that x, okay? And we're going to use that same 5% rule. So if you're calculating percent ionization and you end up with a value of less than 5%, it's safe to say that this x value is so small that it's not, it's not going to change your overall answer much at all. It's like very insignificant. So we're just going to say assumption because X will be small compared to 0.4, we will ignore it. Okay, so now we're going to go about solving for KB just like we would solve for KA. I'm going to set up my expression, the OH negative concentration multiplied by the ammonium ion concentration divided by the concentration of ammonia. Okay, now let me see here. I thought we were given the value of KB. Were we not? Oh yes, we were given the value of KB in the previous question. Okay, so in the previous, like if you flip back a page, I'll just do that just to show you. We were told that ammonia has a KB value of 1.8 times 10 to the negative 5. So we're going to use that so that we can solve for X. So 1.8 times 10 to the negative 5 equals, I'm going to use X's for these guys, and I'm going to use 0.4 for the concentration of NH3. So I'm going to start by cross multiplying. So when I cross multiply 0.4 by 1.8 times 10 to the negative 5, I get 7.2 times 10 to the negative 6. And I'm going to just simplify this instead of x times x to x squared. Then I'm going to solve for x by taking the square root. Okay, so the square root of 7.2 times 10 to the negative 6 is 2.68 times 10 to the negative 3. So the original question says calculate the OH negative concentration. Well, the OH negative concentration is represented by X. So we've just solved for X. So I'm just going to say over here, therefore, the OH negative concentration is 2.68 times 10 to the negative 3 moles per liter. Okay, so not a lot different from what we've done in the past. Now, we're going to also do percent ionization, which we already know how to do. I'm just going to put a little reminder here to check to make sure that the 5% rule holds. There we go. Okay, so percent ionization is equal to, so in this case, now we're dealing with, instead of the hydrogen ion concentration, we want to know what percentage of the entire solution is composed of the hydroxide ion. So we're just simply replacing what we used in the in the Ka questions, we use the hydrogen ion concentration here. In the Kb questions, we'll use the hydroxide ion. So this would be the concentration at equilibrium, because initially the concentration is 0, compared to the initial concentration of the solution. Okay, and then we multiply that by 100% to make it a percentage. So this value here is what we just calculated, 2.68 times 10 to the negative 3. And this value comes from the original question, and we were told we had a 0.4 mole per liter solution. So when we do that calculation, what we get is 0.67%. So that's well below 5%, so we were safe to eliminate that X, which we did prior. Okay, one more problem, and this is just the next type of KB problem, and this would be very similar to the second type of KA problem. Now this one, we're going to calculate KB, and we're given the OH negative concentration at equilibrium. So here you'll notice the question does not give us a specific type of base. It just says the OH negative concentration of a weak base is 4.57 times 10 to the negative 4 moles per liter. If the concentration of the base is 0.3 mole per liter, what is the KB for this base? So let's just write a generic equation here. We don't know what this base is, but we know the base is going to be added to water. I'm just going to include that liquid just so we know we're not going to include that in our ice table because its concentration is constant. And we know a base is going to dissociate into hydroxide and some sort of conjugate acid, right? The hydrogen, this is your acid in this case. The hydrogen from water pops over to the base. So you end up getting whatever this base is, the conjugate acid just has the base plus a hydrogen tacked on to it. Okay, so in our chart, I'm just going to put concentration of the base. Really doesn't matter what it is. OH negative concentration, and then the concentration of the conjugate acid. So we were told the concentration of the base is 0.30 moles per liter. We would start off with concentrations of 0 here. And then we were told the OH negative concentration is 4.57 times 10 to the negative 4. Okay, so because this would all be a 1-to-1 ratio, we can safely assume that this is also 4.57 times 10 to the negative 4. So all we've done here is add that amount for both of them. And we're going to subtract that amount because the concentration of the base is going to decrease while the concentration of the ions are going to increase. Okay, and when you subtract this value from this one, you get 0.2995. All right, so now we can calculate KB. So we're going to take our OH negative concentration multiplied by the conjugate acid concentration divided by the concentration of the base. So let's plug in what we know. 4.57 for both of these guys times 10 to the negative 4. So you can either put squared or you can write them out twice. Either way would work. And we're going to divide by that value. And when we do that, we get 6.97 times 10 to the negative 7. And the question asks us, what is the KB for this base? And that is what it is. We don't know what the base is, but if we had a table of bases, we could figure it out. The table that you have on the front page does not include a KB value that matches this, so we can't really match this up to any particular base. So what you're going to do now is you're going to work on the KB problems just so that you can practice some questions like this on your own.